Hello, everyone. My name is Xinquan Guan, a fourth-year PhD candidate working with Professor Henry Burton in the Department of Civil and Environmental Engineering at UCLA. I'm going to introduce our recent study on the seismic drift demand estimation of steel moment frame buildings. This slide shows a framework for the data-driven model development. To start with, the archetype concept is used to develop a comprehensive database that includes sufficient buildings and their response. The second step is to formulate a model that links the predictors with the target response. Afterwards, a portion of the dataset assembled from the very beginning are used to train and validate the developed models. The next step is to diagnose the model and remove the less important features. The last step is to evaluate the generalizability of the model. This is one of the models developed in this study. In this MLDD model, a machine learning algorithm is used to link the input with the seismic drift demand. After trying different machine learning algorithms, such as random forest, XGBoost, and the neural network, the random forest is found to have the best predictive performance and thus selected in the current study. These two figures show the training and the first layer testing result of the MLDD model. In the left plot, the vertical axis represents the observed drift demand, and the horizontal axis represents the predicted drift demand. The data points are clustered near the diagonal line, which means that the model can capture the relationship between the input parameters and the output. The right plot illustrates the distribution of the relative difference, which follows a normal distribution. The performance matrix D10% and D25% for the MLDD model is more than 80% and 99% respectively, which indicates that the MLDD model performs well. These two plots show the predictive performance of all the existing and newly developed models on the second layer testing dataset. The PSKY model has a lowest performance, which is nearly zero across all intensity levels. The hybrid model, machine learning-based EMKY model, has a highest performance. The performance of all other models falls between these two extremes. This figure compares the predictive performance and the required effort on the part of the user for all models considered in this study. The reduced order MLDD model requires the least effort since it does not rely on any type of structural analysis. Meanwhile, its predictive performance is comparable to the statistically adjusted EMKY model. PSKY requires the greatest effort as it requires performing nonlinear analysis, but it has the lowest accuracy. The effort associated with other models fall between the aforementioned two extremes. Thank you for listening. Please check out our paper and group website for more details of our research work.